Lukas Mueller here today to tell us about higher spin statistics theorem for invertible QFTs.
Yeah, thanks for the invitation. Thanks for coming. Feel free to ask questions at any time. If something is unclear or you want to have more or less details, let me know. So what I want to talk about is somehow an extension of the ordinary spin statistics theorem to more general settings, in the sense that it's a version of what's called higher, so an extension to higher categorical structures or extended operators. But I will spend a decent amount of time just talking about the traditional spin statistics theorem, explaining what invertible quantum field theories are, and then mention where this structure goes. So let me just say what the ordinary spin statistics theorem says. It says, roughly speaking, the following. If we have a unitary quantum field theory, then this implies that the spin of a particle equals the statistics. So these are somehow two different things a particle can have. In general, we should really be careful to distinguish them. But in a unitary quantum field theory, these two things are equal. And now let me somehow say a bit more how to think about this. So I will start with talking a bit about spin. So if we have particles in some theory, they always transform under the orthogonal group SON, or maybe the Lorentz group, which acts on the Hilbert space of our theory. And generally, this action might only be projective, so meaning that what really acts linearly in many settings is the spin group. So the spin group N somehow acts. So this is a projective action in general, and then the spin group acts on our Hilbert space linearly. And the spin group is just the universal cover of the orthogonal group, which has a kernel V2. There's an exact sequence like that. There's the orthogonal group, the special orthogonal group of rotations covered by the spin group, and this acts on our Hilbert space. And now what we can do is we can look at a path gamma, which, or loop gamma, which goes from S1 to the orthogonal group, and this is the loop going through a 360-degree rotation. So explicitly, it's something like somehow a big identity, and then it's some rotation matrix here, so it's called loop pi t. And there's a sign. Oh no, there's another cosine. Right, so this is just a loop which goes through a rotation in SON, and I can lift this loop to the spin group. So I get a loop, a path gamma tilde, which lifts this along this universal curvature, which is now a path from the interval to the spin group. And now I can ask, what's the endpoint of this path? And by this, since this is the universal cover, the endpoint of this path is really the generator of this Z2 subgroup, which I call this generator C. So this is this element C in the spin group, which is the action of this following the path along a 360 rotation. Yes. Oh, I will say something about that later. It's something I will not say much about it. It's something people have in physics. It's a quantum. I mean, most quantum field theories you experience are unitary, but related to having Hilbert spaces, probabilities adding up to 1, these type of things. But so I will actually black box this word a bit and just give you a description of what it is for in the invertible setting, where there is a rigorous mathematical definition. So we have this element C, which sits in the Z2 subgroup, and this acts on our Hilbert space. So we have a Z2 subgroup acting on our Hilbert space, so we can decompose it corresponding to the action. So I just get a Z2 grading, where C acts via the identity on this one and by -1 on this part. So if I have somehow an action of the spin group, what I get naturally is this decomposition. And what it encodes is whether my elements in the Hilbert space pick up a phase if I do a 360 rotation or not. So these things which pick up a phase, some are called transform oddly under this rotation, so they have half integer spin, and the other things which don't pick up a phase are said to have even integer, even spin. So there's this type of composition of my Hilbert space in the theory. So there's one type of Z2 grading. And now in physics, there's another type of Z2 grading, which is the statistics. So generally, there are somehow two types of particles, one called bosons, and if I interchange them, then just nothing happens. So I don't pick up a phase, and this should be compared to fermions, which satisfy some causal sign rule type thing. So if I interchange two fermions, then I pick up some sign. So these two things are somehow what should be distinguished, and mathematically, this is encoded by looking at the category of super vector spaces. So these are all Hilbert spaces. So these are also Hilbert spaces which come with a Z2 grading into a bosonic and a fermionic part. And what makes this somehow different from ordinary Z2 graded vector spaces that we use an interesting braiding on the category. So this is, as a category, it's symmetric, but it comes with an interesting braiding which uses the causal sign rule. So I take two vectors v and w, and if I flip them, I add a sign if both of them are odd. And I mean, this is somehow on homogeneous elements. Okay. And now, so somehow whenever we have a theory, we have these two different Z2 gradings. One comes from the action of the Z2 subgroup of spin, and the other one is the distinction between bosons and fermions. And spin statistics, so I said spin equals statistics, really means that these two Z2 gradings are the same. So a particle is bosonic if it transforms trivially under 360-degree rotation, and fermionic if it picks up a minus sign under the rotation. And the theorem is that if the theory is unitary, this happens. And it's easy to write down examples of theories which are non-unitary and break this type of relation.
That's a question. So, is there like a mathematical formulation of this fact? Because yeah, I mean, really impose some kind of mathematical.
I mean, so
which is sort of has some to do with this unitary QFT, but
yes.
But is there a way to like formulate this actual mathematical theorem?
I mean, one problem is, so I think there's a proof in the white-hat axioms. So there is some, in axiomatic QFT, they can prove this. Then what we will do is, there's a mathematical formulation of invertible unitary quantum field series using things from stable homotopy theory. So that's where we are going to. And then there are also these topological field series, which are somehow in between, where you, and in all these settings, you can prove these statements. But it's.
But you're saying that in terms of white and the axioms actually formulate this theorem?
Yes, I think it's a theorem from the 80s or something, or 90s, like when they did it, yes. But it's somehow a complicated thing. I think I once looked at the proof. I don't remember how it goes.
Yeah, I'm more interested in the formulation.
I see. But I think it's, yeah. But I mean, the problem is just somehow just saying what is a unitary quantum field theory is somehow a hard problem. And then, so yeah, we will somehow look at this in a really specific example. More questions?
This grading comes from this grading we have, right?
Yeah. Yeah, exactly. Just somehow just recording the type of particle. Okay, now I just reformulate this slightly differently. So note that there's this operator which is called -1 to the f, which is, so I look at the category of super vector spaces, and this is a natural isomorphism from the identity to the identity. And as a natural isomorphism, this means that for every super vector space, I need to give you some isomorphism from it to itself. So if I ask what is this at some h, Then it's just a map. So I now somehow use 0 and 1 to denote the grading. And it's just a map which is the identity on H0 and then minus the identity on H1. So it picks up a sign if there's a fermion. So this is somehow counts the number of fermions. And what this means, it's just somehow it's a natural isomorphism from here to here, and it has the property that this squares to the identity. Okay, and what does this mean? Said differently, we can look at the category with one object and the group of the two as automorphisms. And we get a functor from here to the automorphisms of the category of supervector spaces, which somehow sends a non-trivial thing to this natural isomorphism over them. So that differently, this means that there's a certain two group, which is just this thing where we use the that D2 is abelian. So I also can somehow define a monoidal structure on this category, and then this two group acts on the category of supervector spaces via this -1 to the f. Okay. And I somehow want to now explain in a bit more detail that something similar happens on the geometric side as well. So we are somehow now trying to understand what happens if I'm not on flat spacetime, but on some arbitrary curved manifold. And then I don't have an action of the spin group. But what I need, so if I'm on an arbitrary manifold sigma, to define a theory consistently, which involves fermions, I somehow need to make this local structure I have vary over our manifold. And mathematically, this means I want a spin structure. So I want some spin n bundle on sigma, which is a cover of the frame bundle. Let's say I've picked a matrix, so I do like look at the or on an orientation, so I look at the oriented autonomic frame bundle, and then this is a double cover, and it needs to be compatible with the map from spin n to SON. So and then so I need a spin structure is the definition of is specifying such a bundle together with such a map. So in this setting, I cannot act with the spin group on this setup, but what I can do is I can somehow look at sigma, and this has an automorphism, which is just given by acting with the central element in the spin group. And because it's central, this will actually commute with the action, so it really gives an automorphism of the spin structure. So what this means is that for every spin structure, I also have an automorphism of it. So this is similar to the -1 to the f we have seen here. And then, so somehow similarly, next slide. I mean, but I need, this is a spin n bundle. So it comes with an action of the spin group, which acts fiberwise. I can pick the central element in the spin group and act with it. And this is actually an automorphism of the spin structure because it's central. So it will commute with the action of all other elements. It's just something like a gauge transformation, which somehow comes from acting with the central element. So in summary, if I somehow look at some category of n-1, so this is in an n-dimensional quantum field theory, the state spaces are usually associated to n-1 dimensional time slices. So if I look at these things equipped with a spin structure, there's actually another BZ2 action, which is exactly given by this acting with the central element in the spin group. And now my quantum field theory somehow takes such a manifold and assigns to it a Hilbert space or supervector space. So and then I have the other BZ2 action here, which is by -1 to the f. And now the spin statistics relation just means that this field theory Z is equivariant for these two actions, right? Because it somehow says, oh, if I act with C on some Hilbert space, so on the Hilbert space the theory assigns to some surface, then this actually is the same as acting with -1 to the F on the same Hilbert space. So somehow we can understand this relationship between spins and statistics as a quantum field theory intertwining two different actions. And this is what we will generalize later on. So we will take this group and replace it with a larger group so that this restricts to that. But before we somehow extend to higher dimension or higher versions, it's usually helpful to also think about lower things. So this is a two group. So we should ask if every quantum field theory might also intertwine some one group, some ordinary group. And this is also true. So if I look at just some quantum field theory, let's say it's defined on oriented manifolds, and now they are of dimension n. So what I can compute is its partition function. So there's just some complex number, which usually is some integral, ill-defined path integral over some state of space of dynamical fields. But what a quantum field theory should do to certain closed manifolds, it should assign me a complex number. And then here I really mean closed n-dimensional manifolds. Yeah. And then later on there will be Bohr-disms, yes. But so this is somehow just the partition function. And then here on the side of manifolds, I have a Z2 action which reverses the orientation. So this maps M to M bar, which is the manifold with reversed orientation. And over here I have the complex numbers. And I also have a operation which is denoted by bar, which is complex conjugation. So there's another, so there's a Z2 action here, which is complex conjugation. There's a Z2 action here, which is orientation reversal. And now again, if a theory is unitary, as a consequence is we get that the partition function on the orientation reversed manifold is the complex conjugation of the partition function on the original manifold. So there's some equivariance with respect to these other two Z2 actions. So. Okay, so to just summarize a bit what happened so far. So quantum field theory so far is some magical thing which takes as an input some geometric structure and it gives us back some algebraic structure. And now what we have seen is that on the geometry side, we get a natural action of the group Z2 times BZ2, where this acts by orientation reversal and this acts via the spin. Here we find something similar, so we get a Z2 action by complex conjugation and a BZ2 action by the fermion parity -1 to the F. And then if the theory we had is unitary, so this is somehow more a cartoon thing, then the Z will intertwine these two actions. So the geometric action actually agrees with this algebraic action. And what we will do in this talk, or what I will do in the rest of the talk, I try to first suggest an extension of this type of setting and then present a proof in a special case. So just note that this is somehow the one truncation of a certain group, which I call O. So this is the stable orthogonal group. Just take the orthogonal groups in dimension n, and then take the limit when n goes to infinity. And this is somehow called the stable orthogonal group. And if I look at it only at its pi0 and pi1 part, then I get back this two groups. So I get Z2 times BZ2. and the same here. And what we will somehow do is we take both of these actions and we will generalize them to O actions. So we will lift from this, we will somehow present a lift of both of these actions to this larger action of this bigger group, and then we will prove that there's an equivariance between the two things.
Why is, can you explain again why was it easy to action?
So the BZ2 action is this via this fermion grading operator. So a BZ2 action is the same as a natural isomorphism from the identity to the identity. And then here, so this fermion grading operator is exactly such a thing because it will commute with any map which preserves the grading. So it will commute with any map in vector spaces. So it's such a natural transformation. So it gives me a BZ2 action in the category of split. And the spin flip is the same on the geometry side. And then the Z2 action is complex conjugation. And on the geometric side, it's orientation reversal. More questions? Otherwise, so I somehow explained like the first part, what is spin statistics. The next thing I want to explain is what is a QFT, or what is an invertible QFT. And somehow I'm going to not do this in great detail, but what I'm going to explain is what usually goes under the name of functorial quantum field series. And this is going to be sketchy, but I hope to get to the point where things are invertible. And I can at least say what are invertible field series and then state some theorems about them. So, and the idea, I mean, this already comes a bit out from this cartoon here. So we should really think, or this perspective on quantum field theory says that what they do is they somehow representation theory for something geometric. So we have some geometric objects, we apply our field theory, we get something algebraic or something linear. And this is exactly what a representation does. Let me just briefly recall representation, or like what is the representation of a group? I just take a category with one object and my group as automorphisms, and then I can look at functors from this to that. And this is the same as a representation of G. So such a functor just picks out a vector space, the value of a point, and then it gives automorphisms which act on it as the representation. And the idea is just to now, for functorial quantum field theories, to replace this with a different type of geometric object and then use the same type of definition. And the input, this is usually done by defining these Bordism categories, and they often depend on some geometric structure F. This is some geometric structure. And examples are something like orientation, spin structures, but it can also be a metric or a principal bundle with connection, all these type of things. Later on, we will mostly look at things which are topological in a certain sense. This is some symmetric monoidal category, and it has objects which are just n-1 dimensional manifolds. With the structure. And then I want them to be closed. So I want them to be compact and boundary without a boundary, and I want to be allowed to equip them with some geometric structure. And then a morphism is what's called a cobordism. Let me just draw a picture for you. It's something like this, where I have somehow my manifold sigma, which is identified with the boundary of this n-dimensional manifold M. And I have another sigma prime, which is identified with this other side. So morphism from sigma to sigma prime is some n-dimensional manifold M which interpolates between them. And now I can compose these things by gluing. So my if I have two of these cobordisms, what I can do to compose them, I can glue them along this common boundary. And then this composition would just be this manifold, which is now a morphism from here to here. Yeah. How does it work, or could it kind of? Yeah, this is. I mean, right? So I mean, somehow you need to say what F is, and then you need to say what these objects are. We said they're n-1 dimensional things. In the gluing setting, what you should really think of is that they come with some small neighborhood or germ of a geometric structure, and then this tells you how to glue. And the morphisms also tell you how these things go. And I mean, this can be done. This is done in work, for example, of Stolz and Teichner. But also a lot of other people actually spend a lot of time thinking about how to make these geometric things work. And there are these things called extended series where you want to cut along highest codimensions when this gets really complicated. But yeah, it's somehow oversimplifying a bit. If you have actual geometric structures which are not topologically, you need to work with these germs or small colors around them. Yeah. I mean something like a sheaf on manifolds, or maybe depending on what you want, you might even want a sheaf on families of manifolds, because you might want to say, oh, what does it mean for my structure to smoothly vary? So something like that. But it's disjoint union, exactly. This is monoidal by disjoint union. That's the next thing. So the monoidal structure is the disjoint union, and the monoidal unit is the empty set seen as an n-1 dimensional manifold. And now, so what one calls a functorial U of t is a symmetric monoidal functor. And I mean, this is somehow a bit of a sketch than a precise definition from this Bordism category to like super vector spaces. Something like that. And then again, if there's geometry, somehow you want everything to smoothly depend on the geometry. So there's some details which I'm ignoring, and then we can also put other targets here if we want. Are there questions? If not, let me just spell out one of the consequences. So one thing of being monoidal is that if I look at the field theory on the monoidal unit, it's a monoidal unit, which means it's identified with the complex numbers as a vector space. And now if I have a closed manifold M, this is a morphism from the monoidal unit to the monoidal unit in the Bordism category. So I can evaluate my functor on it and get a map from the complex numbers to the complex numbers, which again can be identified with a complex number. It's just a linear map from C to C. So this is what's called the partition function. And now being a functor means that I can somehow take my manifold, and if I want to compute this partition function, what I can do is I can cut it into some pieces. And then to all these pieces, I get linear maps. So here I would get a map from C to the vector space associated to S1, to the vector space associated to 2 copies of S1. So this map is the functor evaluated on this cap Bordism, then I evaluated on this pair of pans, then I can evaluate on these two parts. So I get something to S1 back, and then I get something to C. So, and then this number is just the composition of all these linear maps. So what I can do is I can somehow compute my manifold invariant by cutting and gluing. So I only need to know what the theory does on these building blocks, and then I can compose them to get the partition function. And this is one of the things which formally follows from the properties of the path integral. Yeah. Okay, questions about this type of definition? No, this is a symmetric grading. It's not the usual one, but it's still symmetric, right? Because if I do it twice, I somehow pick up 2 minus 1, so I get 1, yes. So S vector somehow, like Z2 graded vector spaces have two gradings. One is just the flip, and then there's the one with the causal sign. And it's important that you use the one with the causal sign. Yeah. With the causal sign. It's just if you flip two odd things, you get a sign. This is still symmetric monoidal, because if you do it twice, you still get the identity back. Okay. And now it's easy to say when such a theory is invertible. So just, if I have two such symmetric monoidal functors, here what I can do is I can tensor them together pointwise. So I can do Z1 tensor Z2 pointwise. And this for me defines for me a new symmetric monoidal functor. And then we just say Q of t is invertible if it has an inverse the minus 1 under this tensor product operation. And this means something like Z tensor the inverse would be the constant functor at the monoidal unit, which I call 1. And this is an extremely restrictive condition. So one thing it implies is that if I look at the value on a closed manifold, then this tensor product actually becomes just multiplication. And so this means the value on every closed manifold needs to be invertible, in particular non-zero. But where it becomes more restrictive is on state spaces. So if I look at the state space associated to some n-1 dimensional manifold sigma, this means that if I tensor this state space with the inverse state space, I should get something which looks like the complex numbers. And for vector spaces, this can only happen if it's one-dimensional, right? If I tensor two vector spaces together, their dimensions multiply. So these invertible field theories are theories with one-dimensional state spaces. So from some perspectives, they're extremely trivial, which has some advantages, which makes them easy to study. We will also see that they are not completely boring a bit later, but in physics, they show up in two settings. The first setting is for the description of anomalies. If you look at an anomaly, it can often be described by such a theory. And the other setting is what's known as short-range entangled phases in condensed matter physics. They can also often be modeled by these type of invertible quantum field theories. Yeah. Because somehow I say there's this space and I have another vector space so that if I tensor them together, I get C. But now if I tensor two vector spaces, their dimension multiply. Right, so I have two natural numbers which multiply to 1, so they both need to be 1. So as I said, this is somehow slightly restrictive, but it's also what's going to allow us to actually classify these things and work with them.
That's just it's not extended.
Yes. But you can extend these things. And that will happen implicitly at some point. Also, somehow in like 5 or 10 minutes, I will somehow put a specific target which has the property that any non-extended theory into it automatically canonically extends. But these things should really be fully extended. And I mean, also when I give this definition, if F is not topological, I should really work with smooth categories. I had some notes at this part, which I decided to skip. What this thing really should be is like a smooth infinity n category. And then this should be a smooth infinity n category, and you need one smooth functors into them. And then probably even more. But making these things precise is extremely complicated. And in the invertible case, this somehow doesn't really matter. You should think of this more as a heuristic, which is closer to mathematics. I mean, this can be made precise. There are these things, you can study them. There are interesting examples which are not fully extended, like WRT series are not fully extended, and they're still interesting. But yeah.
Smoothness into there in terms of the mathematical.
What I mean with smooth is just that they somehow are fibered over manifolds, or that they are sheaves of categories on manifolds. So I can talk about doing things in families parameterized by manifolds, something like that. But yeah, for now, non-extended. We'll skip this. So and now. So what we want to understand are these invertible series, which go to S vect. And we have seen that somehow the state space needs to be one-dimensional and these maps need to be invertible. So for the theory to be invertible, it beta factors through super lines, and then only the morphisms which are also invertible. This just sits in here. And then I want a theory for this. If this is invertible, it definitely should factor through this category where everything is invertible. And it's not hard to see that this is equivalent to the theory being invertible. So if my theory Z factors through this category of super lines, then it's going to be an invertible theory. And the inverse is somehow just given by taking the inverse pointwise. Okay. Okay, what do I want to say next? Oh, okay. And now this thing is a specific type of category. It's known as a Picard groupoid. So this has some isomorphism classes of objects, which has some pi 0, which is just Z2. So we have an even line and an odd line, and these are all the objects up to isomorphism. And then I can look at the monoidal unit and ask what are its automorphisms. This is what's known as pi 1. So this is C cross. And then there's one more piece of information which classifies this as a Picard groupoid, which is some type of K invariant. So it's a map from pi 0. And then I force everything to have 2 torsion to pi 1. And what this map does, it takes some object X, which I just draw as a line, and then it does somehow uses that X has an inverse. So I do X here, I do inverse here, and then I have an isomorphism to the unit, which is doing nothing. I do the braiding, and then I do this. And in the setting of super lines, you can easily compute that this is just the inclusion of Z2 into Z cross, which sends -1 to -1. This is because the braiding will pick up a sign in this case. And these 3 pieces of data completely classify these Picard groupoids. There's some pi 0, there's some pi 1, and then there's some K invariant. So you should think, oh, this is somehow the same. That's not the same. It's a bit like having a space which only has pi 0 and pi 1, and then you look at its Postnikov tower.
Classified by what?
By a functor from this Bordism category to this category of super. That's the definition, and I'm getting somewhere. I'm not there yet. So I'm saying this category is somehow the same as these three pieces of information.
Like L by 0, L by 1.
Yeah, somehow if I to give you a category which has a monoidal structure, is a groupoid, and the monoidal structure is invertible, it's the same as giving a pi0, a pi1, and a k invariant. It's a bit to give you a space. I somehow can give you a pi0, pi1 up to pi, or the fundamental groups, and a bunch of k invariants. I'm somehow telling you from this data you can reconstruct the category. I have not yet said what these functors into this are, but that's somehow what I want to.
So it's a category with the functor.
Yes.
Functor is classified by give a functor, it needs to give what?
That's what I want to explain
Okay,
next.
that
I haven't explained that yet, but somehow, right, I want to give a functor between two things. I'm just saying this, one of these things I can reformulate in some smaller data, which somehow looks a bit like doing Postnikov decompositions. So we do some type of Postnikov obstructions here. And now the next thing is I have a map into this groupoid. So it will map everything in here to something which is invertible. In here, not many bordisms are invertible. But this map will factor through the thing I get by forcing all the bordisms to be invertible. So this is, I take my bordism category and I force add inverses for all morphisms and inverses for the tensor product. So now this is also some Picard groupoid, which is constructed from this bordism category. And now the first statement is that an invertible theory is the same as giving a map from this Picard groupoid to this one. So I now need to tell you what are maps between Picard groupoids. And you can describe them using this Postnikov data. Yes. I am adding in inverses formally, yes. So this adds in a lot of inverses. Yeah.
The bit that I would immediately get is something from the restriction to the core into that slide. Category.
I mean, so if you would map from here, the core of this would be mapped to the core of this, right? But now I'm mapping into something where everything is invertible. So it somehow will factor through the thing where I add inverses, because the inverses I add here, they will just be sent to whatever the inverses were before. I mean, I'm really applying some adjunction. So I want to map out of, so this is somehow the left adjoint to the embedding of groupoids into categories. And then there's this monoidal stuff I'm somehow not perfectly keeping track of. I'm going to just, because this is not the some of the main focus of the talk, but as I said, these things you should think of them as Postnikov tower or Postnikov data. And then there's a description of functors between these type of things. So if I look at something which goes from P to P prime, so these are now Picard groupoids, meaning that they are, as I said before, they are symmetric monoidal groupoids so that everything has an inverse under the tensor product. Now I can ask, what is pi0? So what are functors up to natural isomorphism from P to P prime? And this is what we want to understand, because these are our field theories here. So there's this pi0. And this sits in an exact sequence. So there's the X group from pi0 to pi1 prime. And then there's HOM pi0 to pi0 prime times HOM pi1 to pi1 prime. So this map somehow is reasonably clear. If I have a functor from P to P prime, I can see what it does to pi 0, and I can see what it does to pi 1. So I get these two elements, but then not all these assignments will work. And then in addition, there's some map here, which goes to pi 0 tensor Z2 into pi 1 prime. And this map is just a pair F and G gets mapped to K prime composed with G. So does that make sense? No, composed with F, sorry, minus G composed with K. So I can either go from here to pi 1 and apply via K, and then I apply G, or I do first F and then K prime. And somehow just spelling out what functors are explicitly, one ends up with such an exact sequence, which we are not going to do. But an easy consequence of this is that if I look at pi zeros of functors from anything into the superline, the core of superlines, then this is the same as maps from pi 1 of whatever the something was to C cross. And why is this true? First, we see pi 1 here is divisible. It means C cross, so this X group vanishes. And then in addition, somehow this map, if I want something in the kernel of this map, it tells me that the map from pi 0 to pi 1 is fixed, pi 0 to pi 0 prime is fixed by what happens with the map from pi 1 to pi 1 prime. So somehow, if I look at something into superlines, it's enough to just look at group homomorphisms from pi 1 of the something to C cross. So the question somehow is, what is pi 1 of this thing? So what's pi 1 of board NF? Which I'm not going to explain in detail, but I just give you what these things are called. Or for topological Fs, these things are known as SKK groups. Or sometimes vector field boardisms, and you can look them up online if you want to somehow know what they are and also how they are defined. Okay. Questions to know? I know this was a bit fast, but somehow the take home is really that whenever you look at these invertible things into S line, it's the same as just starting with pi 1 of the thing you're mapping out of and looking at group homomorphisms into C cross. And physically, this means somehow that knowing the partition functions on closed manifolds determines the full theory, because this map just tells me what is the complex number I assign to a closed manifold. I didn't explain where that comes from. You just spell out what a functor is. And then you literally just write it down using, somehow you first start with this data, you write down the corresponding groupoid starting from it, and then you look at what the functor is, you just spell out all the data, and you will notice that it exactly looks like this.
Pi 1 literally means like pi 1 of the space of arrows considered of the mapping space.
It's just automorphisms of the monoidal unit in this category. So it literally just means that. Yes. I mean, but yeah, this thing, right? Now it's a groupoid. So you should think of a groupoid as something like a space, and then it's pi 1 of the space.
Map.
Okay.
Here, I guess I can kind of see how it's constructed with this S line.
Yeah.
Can you explain what it would be for the board F N, for example? What does it describe?
I mean, it's somehow this picture as a Bordism, right? So you start with some sigma, and then you cross with the circle, which gives you a manifold in dimension, 1 dimension higher. That makes sense. Right, somehow this is a map. So the objects are closed manifolds in dimension n-1. And the pi1 are closed manifolds 1 dimension higher. And this map would take a sigma and literally take the circle and cross with it, which gives the manifold 1 dimension higher. And then you need to figure out. Yes, something like that. I mean, this Z2 somehow just say that this map factors through the thing with things which have order 2. I mean, this is S1, so I map sigma to sigma times S1. The only thing I've been a bit reluctant to say this is that you need to equip this with a geometric structure. And the geometric structure you pick somehow comes from doing this flip. So depending on what your flip is, this might look differently. Like there's some geometric structure type thing. But yeah, it's more or less crossing with S1. It's just a question what geometric structure you pick on S1. Like in the spin case, S1 has 2 spin structures. And I should be able to tell you which one you want. I think you want the non-bounding one. Yeah. Where are we?
So you're transferring with Z2, is this because you're like symmetric monoidal or?
Yes. Is that symmetric monoid? I think the Z2. I think I'm just going, what I want to say is that the image has order 2. And this comes from symmetric monoidal, yes. Yeah. Okay. Yeah, might be a good time for a break.
Yeah, 3:10. Do that.
Should be taking copy of
Reference for these card voids in general. Like, is there a paper that says if I have like a symmetric monoidal in category, the automorphism group of the.
So for one category, I think it's a bit, these things are a bit hidden. There's some unpublished work by Stolz and Teitner where they do this in great detail in an appendix, which is not that helpful because you only get it if you email them.
I guess.
You can email them, you can ask them, you can say that I mentioned that, but
because I'm studying a Picard group for something that's a bi category.
I see.
And it was like a general theory behind this thing. So
I mean, right, what this is really a 2-term spectrum, or a spectrum of pi 0 and pi 1. I think there's a good general theory for like these type of things for spectrum, like Postnikov. Can you read about this? I don't know. This is Dan Fried has these notes, which are called Bordisms, old and new.
Okay.
He talks a bit about spectra of Picard group poles.
Okay.
So this thing I was saying is in there. That might be a good place to start.
So the idea is you just view this, like the Picard group, which should always be some spectrum. Here, this is like the
Just
one
like,
truncation.
it's like, yeah, Picard group pole is something. What to say that? That's Should I continue? Okay. Yep. So thanks for coming back. James said the second half can be as technical as I want. So my things might get a bit more technical now. Might also be a bit more rigorous. So the first thing, I mean, people were already complaining about this. I somehow defined a one category of Bordisms. What I should really have done is move to like an infinity categorical setting, where the Bordisms are described by some infinity n category. So this is now, this is now an infinity n category where I'm both allowed to cut down to points, but I also consider topology on spaces of manifolds or diffeomorphisms as hieromorphisms. But the definition of invertibility still carries over. I have some target, I can look at its core, and I can ask this to factor through the core. So I still can have this type of setting, and I will still end up with this localization. So now this is some infinity n category where all morphisms are invertible. And then in addition, it has some monoidal product, which is also invertible. So the first thing we will use is The homotopy hypothesis says if I have an infinity group void, so something where everything is invertible, I should just think of this as a space. And then the points in the space are the objects, the paths in the space are my morphisms, homotopies between paths are two morphisms, and so on. So we think of this as a space, but in addition, it has some multiplication, which came from this being symmetric monoidal. So we have some symmetric monoidal multiplication on our space, which is commutative. So I have a commutative multiplication on a space, which is group-like. Yeah, so what I wanted to say, this is somehow the space. And then it has some commutative multiplication, which I just call an E infinity multiplication. And then we can use a theorem of May from the 70s, which says that this is the same as this thing being an infinite loop space. So this implies this thing is an infinite loop space. So somehow having this commutative multiplication is the same as being an infinite loop space. So what this means is that there is a space called X1, such that if I look at loops in X1, it's homotopy equivalent to the localization of our Bordism category. And then this space X1 is homotopy equivalent to loops in some space X2, and so on. X2 is loops in some space X3, and so on. So this is really, yeah, infinite loops on something. And if you have a loop space, you can compose loops. So there's some composition. And then if you have more and more loops, it will just become more and more commutative.
Go for board and board at 0. We formally inverted cobordisms.
I mean, a lot of things happened here. I'm sorry. So there was board n. This is a 1 category. Now, this is really an infinity n category. So I did two things. First, I added higher morphisms corresponding to diffeomorphisms. And then I also I allow to cut my manifolds again. But before we had cobordisms, and now I allow to cut them so that I get manifolds with corners. And then I allow to cut down to the point. I just add these things as new layers of my morphism. So objects in there would be points. One morphisms look like this. Two morphisms are Bordisms between one morphism. So might be something like this. This would be a two morphism from the one morphism at the bottom to the one morphism at the top, and then so on up to n. I mean, I just define a larger category which somehow reduces to this one if you both restrict to the endomorphisms of like the identity on the monoidal unit. And then I also somehow, if I take pi 0 to the space of morphisms, I get this thing back. And somehow, this is the more fundamental object where you get the old thing back by applying various simplifications to it. But then we localize, so the thing we get is actually going to be is infinite loop space. So it's not a fancy thing. I mean, it's a bit of a fancy thing, but it's not as fancy as a symmetric monoidal infinity n category. It's something which people in the 70s were able to study in topology. So it's just an infinite loop space. So it's some space which is loops in some other space and so on. And this being loops just in quotes having a multiplicative, like a tensor product which is symmetric. I mean, this is just a symmetric monoidal structure on here. This will induce an E infinity structure. This is just, you should think of them as being the same word somehow. Then you should think of them as being an infinite loop space. In this case, that's good enough. So it's loops and loops and loops. Okay. So I'm adding diffeomorphisms as n plus 1 morphisms, then isotopies of these as n plus 2 morphisms, and so on. So what I really do is, there was a set of Bordisms here, and I replace this by the space of Bordisms. And then the space has some paths, which I think of as like morphisms of the corresponding degree. Okay. No, how much time? Yeah, I think I will probably not say that much about these things. But this type of structure, it also has a different name. It's known as a spectrum. So these infinite loop spaces, or more explicitly, if these are connected spectra. I was thinking about saying a bit about what they are, but you should just think of them as a family of spaces x0 up to infinity, where I have these identifications between xi and loops of x of one higher. Okay. So you should just, exactly think of them as algebraic topological to describe infinity groupoids with an invertible monoidal structure. Okay. I think I'm skipping an introduction to spectra. It's somehow, for what I'm going to say, it's not going to be that relevant. There are also good notes on these online. So yeah, if you don't know what they are, I hope you can still follow at an informal level. So the other thing, somehow I said field theories are functors to super vector spaces. But now I put some higher category there. So what's a good target? What's a physically sensible target? And one of the problems, or I don't know, it's just something we don't know at the moment. And for TQFTs, there are some suggestions, but there's nothing really rigorously written down. But for if I restrict to these simpler invertible series, there's a proposal by going back to Mike Hopkins, which says that somehow the thing we saw over here is just what we can generalize. So we call that we somehow functors into our target superlines, which just maps from pi1 to C cross. And we can now define a spectrum, which I call sigma n I C cross, and it's called this somehow the Pontryagin. It's called the Pontryagin dual, and I define it by just taking this definition and extending it. So I somehow say the space of maps from some other spectrum into this spectrum is just the same as, and I put a sigma n here, so it's homomorphisms from the nth homotopy group of my spectrum into C cross. So this is also known as the Pontryagin dual to this group. So I somehow just define a spectrum by this universal property, and now one needs to check that this actually leads to a spectrum, and one way of checking this is checking that this defines a generalized cohomology theory. That's what was originally done. And I mean, so it's somehow this thing is defined through this universal property, which just extends the property we had here. This is all stuff about spectrum. And now, somehow, if I truncate the spectrum at 2 levels, I get the core of superline spec. So if I restrict to things which fit into what I was saying before, it reduces to these things. I don't think so. What do you get? You definitely don't get K-theory. I don't know. A good question. I should know.
For any, I mean, you don't have contract.
I mean, there's if n is 1, I have pi1 of x and map to C cross.
Contract will still make sense.
Yes, because this is a spectrum, so all its homotopy groups are abelian. Somehow it's infinite loops in something, so like somehow pi1 of it is still going to be abelian.
X be the spectrum itself.
X is a spectrum, yes. I define a spectrum by saying what maps out of it are. So I'm just giving maps into it are. So I'm giving some universal property, which I need to check that there's something satisfying this. And somehow one way of checking that something is a spectrum is just seeing that maps into it define a generalized cohomology theory when I evaluate on spaces. Oh, yeah. So there's a map from spaces to spectra, which is like an infinite loop space type construction. Yeah. And then let me maybe skip. Let me just say sometimes people also like to look at this thing, IZ1, which is the Anderson dual to the sphere spectrum, which relates to deformation classes of series. But which is described by a similar universal property, but I somehow take this thing, this group, which I've considered as a discrete group now, and I put a topology on it, just the topology it naturally gets. And if I do this, I somehow end up with the spectrum, which is called IZ1. And then and the one doesn't mean anything, it's just sort of convention people put there. Okay. So now what I want to do apparently is define for you the higher statistics action. So I want to define an action of ON of the stable orthogonal group on these two spectra. So let's just start with something reasonably easy. The orthogonal group X on Rn. And then I can go to the 1-point compactification. So what this means, if I pick an element in ON, I get a map from Rn to Rn. If I do a 1-point compactification of this, I get a map from a sphere to a sphere, which is the same as a point in the loop space. Let me say, so from this, I get a map from ON to the n-fold loop space of the n sphere. And they are compatible with suspension isomorphism. So from here, I have an embedding into ON plus 1, which just doesn't do anything to the n plus 1's component, leaves this invariant. Here I have a suspension isomorphism. Not isomorphism, I have a suspension map, and this diagram commutes. So what I can do is I can take the limit which sends this to infinity. And then I get a map from O, from the stable. So I take this construction, and I take the n to infinity limit. And this will give me a map from O to what's known as the sphere spectrum. So this is just a spectrum where the n space is just the n sphere. So and then the maps are just the maps between the suspensions. And then it's not going to satisfy these isomorphisms between loops in it and things in one dimension lower, but you can complete this into a spectrum. This is sometimes called a pre-spectrum. But there's a spectrum corresponding to the spheres, and this classical construction gives me such a map. And this classically is known as the J homomorphism. So this map is sometimes called a stable J homomorphism. And then differently, so I have a map like this. And now what I can do is if I have some other spectrum, if I have S, I have a map from O times S. I can go to the sphere spectrum tensor with the sphere spectrum. This is the tensor product in spectra. And then, so what this should really be is, no, that means, okay, this is just, let me just say this goes to something like spectra times spectra. And then what I can do is I can use the smash product of spectra to map to S. So I have a map to the sphere spectrum smashed with the sphere spectrum, which is just a wedge of spaces extended to spectra. And then the sphere spectrum is the monoidal unit for this. This goes back to the sphere spectrum. Oh. Put differently, we have a functor from BO to the category of spectra, which is called the J homomorphism, which sends the point to the sphere spectrum and then an element of O to this action on the sphere spectrum. Okay. And this is somehow just what this classical construction here induces at the level of spectrum. And I mean, this was somehow extensively studied by Adams, because this is more or less the spectrum representing K-theory. So you can ask what you can see in the stable homotopy groups of spheres coming from K-theory. Okay, how does this connect to what we were doing? I can now just use this J homomorphism to define an action on any spectrum. So I have a map from BO to spectra times spectra. So X is some spectrum. And what I do is I just do J, and then I cross with X. And now I can do the smash product to go to spectra. And then this will map the base point of BO to the sphere spectrum wedged with X, which is just X. So every spectrum has an action of the stable orthogonal group through the J homomorphism. And now we just define the higher spin as a higher statistics action.
Okay, first conference.
It's J with a subscript X, and X is some spectrum.
What is not from the spectrum?
One is just a J homomorphism, and the other one is just a constant map at X. So it doesn't do anything in the second component. And then I wedge them together, and then this isomorphism somehow acts with what the J homomorphism does on the spheres on the spectrum. Makes sense. Okay, and now the higher statistics action is just defined by, let us do I now replace the C cross with a U1 for some technical reasons I don't want to get into. And then I take its inverse. So BO is a space, but in addition, it's an abelian group where the sum comes from direct sum of vector bundles. And so I can take the inverse with respect to this addition. This is what I call minus J. And this defines an action on IU1, as it does define an action on any spectrum. And now, and we had, if we are in n dimensions, we add the suspension. So I can now just observe, or one can observe the following thing, which I'm not going to explain in detail, but if I look at the super line, the groupoid corresponding to super lines, this is the 0,1 the 0,1 truncation of, I mean, doesn't matter, let me take C cross. And then if I ask what is the minus J action on here, it's exactly the action of complex conjugation and fermion parity we have seen before. So J, so observe if I restrict to reproduces. So this part one. So this reproduces what we've seen before. And now one interesting question one can ask is somehow what happens in higher degrees. Oh, I should maybe not erase this, sorry. And the next non-trivial degree is
I can ask you a question. So, minus succession. So what does that have to do with like bosons and fermions?
I don't know, but if I restrict to this, it recovers the distinction between bosons and fermions.
How do you see that?
It's a computation. You compute what the J homomorphism does on superlines. So you essentially compute
But
the K invariance.
what is actually the state?
So well, the statement is something like Z2 times BZ2 acts on superlines. And the action of BZ2 is via -1 to the f. This detects which parts of the supervector space are bosonic and which ones are fermionic. And the statement is, if I use this identification, minus JIU1, if I restrict this to pi0 and pi1, exactly recovers this action. And I don't have a conceptual reason for this. It's just a computation you can do. I mean, the conceptual reason, if you talk to someone like Theo, he would tell you what really is happening is that this is some type of higher Galois group, and this is what fermions were supposed to be. And then this is somehow what this recovers. There's some story of algebraic closure in higher category theory, which somehow should tell you why this is the right thing, but you should ask other people about that. I mean, here, it's really a computation that if you compute what -J does on the core of superlines or on this truncation, you recover this previous action. So in particular, I have no idea what the pi3 action means physically. Like it's, I mean, this is an action of the stable orthogonal group. So there's a pi3, right? So this is what I wanted to say. Pi3 of the orthogonal group acts on this Anderson dual. So it acts on something which you should think on some type of 2 category, which the theory would assign to things in codimension 3. And there's some Z action on these things, which should tell us something. And yeah, I don't know what this means physically. I'm somehow now only doing mathematics. And it would be extremely interesting, at least for me, to understand what's going on. So that's what I want to say. Pi3 of the orthogonal group is the integer, or just the integers. And now this acts on the spectrum IU1. So I can look what this spectrum has some homotopy group in degree -3, which is Z mod 24. So this would say something like in this degree, somehow what were bosons and fermions before, there are now 24 types, which are something. And then it says, if I now act with this pi3 on this, there's a map from here to pi0, which is just U1. So there's some map going from Z mod 24 to U1. And this map turns out to be the inclusion at the generator. Oh, okay. So let me just recall what we did so far. First of all, we took invertible series and reformulated them in terms of maps of spectra. And I've constructed an action of the stable orthogonal group on here, which is just the inverse of the J homomorphism. Okay. So this is what I call higher statistics. And I really only know how to act on the spectrum. I don't know what to do if it's not invertible. I mean, I don't even know what a good target is. So I don't know where it should act on. But if you talk to Theo, he would tell you that this O is part of the Galois group of some higher algebraic closure. But yeah, I'm somehow not qualified to say much about this. But this is what we did so far. And now what I will do in the last 20 minutes or so is I will also construct an action of O here, which I call higher statistics. And then I will show that if the theory is unitary, this will be equivariant. Questions? What? Of the stable orthogonal group on the spectrum. I mean, I will even construct it on this category, infinity n category, which then will restrict to an action on the spectrum by just localizing.
Or what is this map?
This would be an invertible field series.
This is
Yeah. And then not every invertible field theory will intertwine these two actions, but if it's unitary, it will.
so you're saying that this should be the target. This is like an appropriate target.
This is what it's an appropriate target for invertible things. So somehow, whatever your good target is, its invertible part should look like this.
Comment was that you don't know what the target
Yes,
for a general,
yes.
but you know what the target.
Yeah, because I somehow just generalized this universal property that the partition function characterizes the field theory. Yeah.
Why should it spectrum be a target? So I would think it'd be some sort of like category sense iterated here.
But if it's invertible, you only see something which is invertible, right? And then it will naturally be a spectrum. So somehow there should be some non-invertible thing, which is a higher category. And if you look at its core of invertible objects, then you should recover the spectrum. And I don't know what the thing is, which has this as a corresponding spectrum, but I somehow people have been knowing for a while that this is a good spectrum to look at.
This you mean this you were just responding was some kind of universal property of the character spectra, right? Or nothing.
Yeah, I just define a spectrum by a universal property.
The thing about spectra being good target
Yeah.
is because this universal property of the character spectra.
I think it's just if you take things which are infinity n category and you make things invertible, then you automatically do things in spectra. It's just some adjunction between them. Okay, now what I want to do is I want to define an O action on this Bordism category, at least in a nice class of cases. And now we are also wholly in the topological setting, because that's the only place where I really know how to do that. So I require my F here to be locally constant. And then, so if it's locally constant, I know what it does globally if I know what it does on a disk. And what it does on a disk, it's enough to know what it does on ON. So what the action of the automorphisms are. So this setting, giving a tangential structure is just giving a functor from BON to spaces, which I can straighten to just giving some space xn over BON. So if I have a space xn over BON, this defines for me a topological structure I can put here, which is known as tangential structures. So this includes things like spin or orientations. And what they are is I just start with M. I look at the map classifying the tangent bundle. I have my xn, and then a tangential structure is a lift of this map and some homotopy filling the square. So this is what a tangential structure is. And I can look at a Bordism category with these tangential structures. And I call a tangential structure stable if I can build it from some space X, which sits over the stable orthogonal group by pulling back to BON. And these are somehow tangential structures which come in families. Examples are spin. Somehow it makes sense to talk a spin structure on a manifold of every dimension. And the thing here is just the stable spin group sitting over the stable orthogonal group. And then this recovers topological spin structures. Okay. And what we want to do is we want to build an action of the stable orthogonal group on this category. And this is a complicated category. So it's not possible to do this by hand. But what you can use is that it's functorial in F. So it's So instead of acting on the full category, I just act with the stable orthogonal group on Xn as a space over BON. And then this action somehow will translate to an action on the Bordism category. Mhm. Okay. So what I want is a map from BO to spaces over BON. Right, this is an action of BO on a space over BON. It's an action of O on a space over BON. And now I can somehow it's a space over BON. It's a map from BO into that. I can rewrite this equivalently as a space X triple N, which sits over BON times BO. Such that, and now I want to not act on an arbitrary space over BON. I want to act over my original X. So what I want is if I pull back to BON, I get Xn back. So this is what I want to build. I want to build a space sitting over BON times BO, which if I pull it back to BON, I get my Xn back. Okay. And there's a simple way of building such a space. So I take BON times BO. I have a map to BO, which is just, right? We remember that this was an abelian group. So I can take the inverse, and then BON maps to BO, BO maps to BO, and I take the inverse. So there's this map which takes the inverse of these two things. I have my stable tangential structure sitting over BO. I pull it back, and this is my X tilde N, which sits in this pullback. And now I can ask, oh, what's the pullback to BON? And we see that just because pullbacks compose, it's a pullback of this map, which is just the inclusion of BON into BO. So this is the XN. So this will give some mysterious BO action on the Bordism category. And again, we can somehow observe that if we restrict this to the one truncation, we recover both orientation reversal and the spin flip we have seen before in the example of spin. And the orientation reversal was already observed in a paper by Fried and Hopkins. Okay. And now I'm doing better on time than I thought. So if there are questions on time. Okay, now I want to talk a bit about unitarity. Right, the spin statistics theorem says something happens if a theory is unitary. So what does unitarity mean in this setting? I'm not going to give you a definition. I'm just somehow going to give you a theorem which then you can think of as a definition, but there's a better definition underlying the whole story. So let me first state a theorem which is due to Galatius, Madsen, Tillman, Weiss, and then a slightly different version which looks at this fully extended series due to Schumacher-Priest. Oh, this is 09. This is 24, which says, so what is, so I compute this localization of the Bordism category. And it says, like, if I look at the spectrum corresponding to this is it's what's called a Madsen-Tillman spectrum. And then I use another theorem which gives a categorical description of this type of the spectrum. It just says this is the co-limit over Bxn of a functor from Bxn to spectra, which is the functor I map from Bxn to Bo or Bon, and then I map to spectra by doing the inverse of the J homomorphism. And the co-limit of this functor over Bxn reproduces the spectrum, which is this localization. But these spectra also have an explicit description using tome spaces. This is some virtual tome spectrum, if that means something to you. But it's an explicit construction of this, the corresponding spectrum. Oh, I forgot there's a suspension here. So these structures somehow are, these spectra are geometrically well defined, and its homotopy groups are closely related to Bordism groups. So we know a lot about these structures, and you can really study them using classical geometry. And then what we can do is we can look at a spectrum where we send n to infinity. So we define the spectrum mtx as the limit n goes to infinity of these spectra we had before. And they embed into each other, for example, because the Bordism categories embed into each other. And then there's this, we move to a different blackboard. There's an important theorem due to Fried-Hopkins, which says that an invertible field theory is unitary if and only if it factors through the stable version. So there's a theorem by Fried and Hopkins. On 21, which says an invertible field theory MTXN, let me just do U1, is unitary if and only if it, if it factors through MTX. So what does this mean? We have this map from sigma n MTXN. There's a map here to MTX. I have my unitary, I have my field theory here to IU1. And this Z is unitary if and only if I can find a map here, such that the diagram commutes. And I'm not going to define what unitary means. I'm just using this statement as a definition. But there's a lot to say about this. And unitarity just means it factors through the stable version. What?
What did they take?
Yeah, that's what I don't want to explain. I also, yeah, there's a, yeah, it's a bit involved. It's so there's some, one thing is equivariance with respect to the two part of the O action I described. So this is something which is called reflection. And then it's a certain statement about things lifting from Hermitian. There's something which looks like a Hermitian line, and you want this to lift to something which looks like a Hilbert space. And that's the other condition. Yeah.
But why? Like a maybe related to stability.
Oh, I think this is a weird coincidence in the stable case. Because that unitary, it's a weird coincidence in the invertible case, that unitarity is related to extending to higher dimensions, right? Here what happens is this n-dimensional theory is unitary if and only if I can somehow extend it to manifolds of arbitrarily high dimensions. This is what this means. So I can somehow evaluate it on Bordisms 10 dimensions higher, and it will give me some relations. I think this will not be true. Like somehow if you have this, you are forced to be invertible. So I don't think this is something it's related to. Yeah. It's somehow more, it's some weird coincidence about how these things are defined as colimits. That's really what's happening. So for example, for topological field theories which are not invertible, we at least have a decent guess of a classification of unitary ones, and there somehow they don't extend up. So it's really just something which in the invertible case somehow seems to agree. And I think it's surprising and might be a bit misleading to assume that this is a general effect thing. Yeah. And now I'm just going to give the proof of the higher spin statistics theorem using this as an input. Because the proof actually is quite easy. The setup is a bit involved, but proving the statement is mostly formal. So what do we have? We have a field theory which is invertible. Mapping to IU1. And what we want to show is that I have this action by minus j here. And I have this action, let's call it alpha xn on here. And I want to show that it's equivariant with respect to this. And I use that it's unitary to show that I can factorize through the stable version. So I get this. Here I act with alpha xn. On here I have a stable version of this action, which is alpha, which I call alpha x. Now on here I also can act with the inverse of the J homomorphism. Now this is on I sigma IU1. Here I can act with J for the stable thing MPX. Now spectra have this property that every map of spectra is canonically equivariant for the J homomorphism. So it's also canonically equivariant for minus J. So now the proof just happens by showing that this action is equivalent to this action. And somehow by construction, this map is equivariant and this map is equivariant. Okay. And then how? So how do we figure out what this action alpha x is? For this, use one more small idea. Okay, sorry. So first we need to figure out what this thing is in the stable case. So if I look at BO times BO, mapping via minus to BO, I have X sitting over here. And I want to compute this pullback. And this pullback turns out to just be X times BO. And this type of splitting only happens because it's stable. And the map, so let's call this map rho. Then the map down here does rho. So let me, X is an element in here, an element in there I call V. So does rho plus V, comma V. And then if I go around like this or this, the V's will cancel out. So this is a pullback. And now to compute the action. Somehow use the description of the functoriality via Kahn extensions. So I take the data I have there, I rewrite this as a fibration. Then here I have the map on the first component over there. So I do rho of X plus V. This goes to BO. I do minus J to go to spectra. And then the action on MTX is just left Kahn extension along this map. So this is what I want to compute is left Kahn extension of this map. And we can compute it using the pointwise formula for left Kahn extension. So this is just a colimit over X but it's a co-limit over the fiber. And it's a co-limit of minus j rho of x plus v. So this is at an object v in BO, at a point in BO, and then I use that j somehow sends direct sums to smash products. This just be, and that wedging preserves co-limit. So this becomes co-limit over x minus j rho of x wedge minus j of v. But now this co-limit by definition is just empty x. This is just the same as empty x wedge minus j of v. And this is exactly the action of, right? Somehow doing this was exactly the action of the J homomorphism on the spectrum. So we've seen or sketched that the action alpha here actually is identified with the action of minus J. And I know that this is intertwines the two alpha actions. This map will intertwine the two J actions. So the composition will exactly satisfy this equivariance for spin and statistics. Okay. So this somehow completes the proof, and it also completes my talk. So thanks for listening.